Welcome back. In this lecture I shall begin a very important topic in air conditioning, that is heating and cooling load calculations. I shall begin this lecture with a discussion on solar radiation. So the specific objectives of this particular lecture are to introduce the need for load calculations, discuss the importance of solar radiation in air conditioning, discuss solar geometry, present methods for estimating solar radiation on any surface. At the end of the lecture you should be able to explain the importance of solar radiation in air conditioning, define and explain various terms related to solar radiation, calculate various basic and derived solar angles, and finally estimate direct, diffuse and reflected radiations on any surface. So let me give a brief introduction. Why do we have to carry out cooling and heating load calculations? Cooling and heating load calculations are carried out so that the equipment designed or selected serves the basic purpose of air conditioning. So this is a very important activity. From the load calculations one can estimate the capacity that will be required for various air conditioning equipment. And actually cooling and heating load calculations is a very stepwise procedure. It is a systematic stepwise procedure. You have to have certain inputs like the specifications of the building, the load pattern and all that, and from these specifications you have to calculate various energy flows across the building. Okay. For example, energy transfer to the building or energy transfer from the building, energy generated inside the building, etc. Okay, so from these, at the end of these this stepwise procedure, what you get is the total load on the building. Okay, so this total load on the building is required in order to estimate the capacity of the cooling or heating equipment. Okay, this is the purpose of cooling and heating load calculations. Okay, so why do we have to bother about solar radiation in air conditioning? What is the importance of this? It is important to understand the various aspects of solar radiation because a major part of building heat gain is due to solar radiation. So in order to estimate cooling and heating loads, one has to take solar radiation into account. And second reason is that by proper design it is possible to harness solar energy beneficially, thereby reduce the cost of air conditioning system. This is very important reason also. And the third reason is that in certain instances it is possible to devise cooling and heating systems that run only on solar energy. Okay, so this is a very important. This is very important as far as energy conservation is concerned, because it is possible in some cases where you can have a cooling system. For example, using an absorption refrigeration system, you can devise an air conditioning system which runs only on solar energy. Okay, so it does not require any other energy input. So this is very beneficial as far as certain remote areas are concerned, and it is also very good from energy point of view and also from environment point of view, because solar energy, as you know, is renewable and it is very non-polluting. Okay, so you have to understand the solar radiation properly so that you can use it properly to reduce the load on the equipment, the load on the heating and cooling, so that you can go for a smaller equipment which will reduce the initial and running costs, and you can also design systems which use solar energy. Okay. First let me give a very brief introduction to solar radiation. As you know very well, the sun, which is nothing but a star, is treated as a radiant energy source with surface temperature that is equivalent to that of a black body at 6000 Kelvin. Okay, so this is equivalent to a black body of surface temperature which is approximately equal to 6000 Kelvin. Now the spectral distribution of solar radiation is given in the table here. So you can see here that the solar radiation stretches from about 0.29 microns up to about 4.75 microns, and it consists of invisible ultraviolet radiation which lies in the wavelength band of 0.29 microns to 0.4 microns, and it consists of about 7% of the total radiation. And the visible radiation, which lies between 0.4 to 0.7 microns, consists of about 39% of total solar radiation. And the near infrared radiation, which is in fact gives rise to heating effect, lies in the range of 0.7 to 3.5 microns, and it consists of about 52% of the total radiation. And finally you have far infrared or FIR radiation, which lies in the range of 4 to 4.7 microns, and it consists of 2% of the total radiation. So, you can see that the majority of solar radiation lies in the range of visible radiation and near infrared radiation. Okay, so almost 91%. That is the reason why the sun is a major source of light as well as heat. Okay. Now let me define what is known as a solar constant. A solar constant is the flux of solar radiation on a surface normal to the sun's rays beyond the Earth's atmosphere at the mean Earth-Sun distance. Okay, it is important to understand this definition. It is nothing but the solar radiation per unit surface which is kept normal to the sun's rays and which is kept beyond the Earth's atmosphere. Okay, and at the mean Earth-Sun distance. Though this solar constant value varies with time from day to day, the currently accepted value is about 1370 watt per meter square. Okay, so you can use this value in calculations. And what happens to the solar radiation as it enters into the environment or as it enters into the atmosphere? In passing through the Earth's atmosphere, the solar radiation gets depleted due to reflection, scattering and absorption. So, we know very well that the atmosphere, Earth's atmosphere consists of various gases, it consists of water vapor, it consists of several dust particles of several sizes. Okay, so atmosphere consists of all these things. So, as the solar radiation enters the atmosphere and as it passes through the atmosphere, it gets reflected, it gets absorbed, it gets diffracted. Okay, so it undergoes all these processes as it passes through the Earth's atmosphere. Okay, so ultimately the end result is that even though the solar radiation or the solar constant is 1370 watt per meter square beyond the Earth's atmosphere, as it arrives at the Earth, it gets depleted considerably because of the presence of the atmospheric gases, dust particles, water vapor, etc. Okay. And the extent of depletion depends on the composition of the atmosphere and the length of travel of sun's rays. Okay, so obviously the composition of atmosphere has a great effect on the extent of depletion, and it also depends upon the length of the travel of sun's rays. And the length of travel depends on what is known as altitude angle. So I will define this altitude angle a little later. Now let us briefly look at Sun-Earth relationship. We know that the planet Earth makes one rotation about its axis every 24 hours and one revolution about the Sun in a period of about 365.25 days. Earth's equatorial plane is tilted at an angle of about 23.5 degrees with respect to its orbital plane. This is very important. For example, in this figure you can see that this is the Sun. Okay, and this is the Earth. So, Earth is orbiting around the Sun, not in a circular this thing, this is slightly elliptical, and it is tilted at about 23.5 degrees centigrade with reference to its own axis. So, it is not perpendicular, you can see that it is slightly tilted. Okay, this is the pole, north south pole of the Sun, so it has a tilt, right. So, this angle is about 23.5 degrees. Okay, and you can see the position of the, if you take the Sun as a reference, then you can see the position of the Earth at different days. For example, at on June 21st its position is like this, and on September 21st it is like this, on December 21st it is like this, and on March 21st it is like this. Okay, and June 21st is known as summer solstice, and September 21st is known as autumnal equinox, and December 21st is known as winter solstice, and March 21st is known as vernal equinox. Now, if you look at this figure, you will find the tilt and what is the effect of the tilt. Okay, for again you can see that there is this angle is 23.5 degrees centigrade, and on June 21st this is your northern hemisphere and this is your southern hemisphere. Okay, so on June 21st the northern hemisphere is tilted towards the Sun. Okay, whereas the southern hemisphere is tilted away from the Sun. So as a reason you find that the northern hemisphere experiences summer during this season. Okay. Similarly, when you come to December 21st, this is the northern hemisphere, this is southern hemisphere. Okay. Northern hemisphere is tilted away from the Sun, whereas southern hemisphere is tilted towards the Sun. As a result, this experiences winter, okay, the northern hemisphere, whereas the southern hemisphere experiences summer. Okay. So the seasonal variations are mainly because of the tilt angle. Okay. So, as you know very well, the earth's rotation is responsible for day and night, whereas its tilt is responsible for the change of seasons. Since the distance between earth and sun is very large, for all practical purposes it can be considered that the sun's rays are parallel to each other when they reach the earth. Okay, so the distance is about 93 million kilometers, so it is very large. So, you can consider the sun's rays to be parallel when they reach the earth. Now, we are interested in the solar radiation striking a surface as far as the air conditioning load calculations are concerned. So, let us see how to calculate this. The rate at which solar radiation is striking a surface per unit area of the surface is called as the total solar irradiation on the surface, and the total solar irradiation on the surface is given by this equation: I subscript I theta is equal to I subscript dn cos theta plus I subscript small d theta plus I subscript r theta. And as you can see here, I subscript I theta is the total solar irradiation of a surface in watt per meter square, and I subscript capital Dn is the direct radiation from sun, and I subscript small d theta is the diffuse radiation from sky, and I subscript r theta is the reflected radiation, and theta is known as angle of incidence. Okay. So, you can see that the total radiation incident on any surface consists of basically three parts. One is because of the direct radiation, the second part is because of the diffuse radiation from the sky, and the third part is because of the reflected radiation, okay, from the ground and from the surrounding surfaces. On a cloudless day, that means when the sky is cloudless, you find that the contribution of the direct radiation is about 85%. So, of the total radiation. So, the contribution of diffuse and reflected radiation is quite small on a clear day. Okay, whereas on a cloudy day you find that the importance of or the contribution of diffuse radiation increases, whereas the contribution of direct radiation reduces. Okay. Now, what is the angle of incidence? How is it defined? You can see that the angle of incidence is nothing but the this is the sun's rays. Okay, this is your sun ray. Okay, and this is the surface on earth, you can see here, and this is a normal to the surface. Okay. So, the incident angle is theta. Theta is nothing but the angle between the sun ray and the normal to the surface. Okay. So, this is this angle, right. Now, the incident radiation depends on solar geometry involving several basic and derived angles. So, it is important to understand these angles. And what are the basic solar angles? The basic solar angles are, the first one is what is known as latitude, and the latitude indicates the location on earth. So, what is this latitude? The picture here shows northern hemisphere. This is your northern hemisphere, this is your equatorial plane. Okay, so this is your equatorial plane, and O is the center of the earth, and O dash is the center of the sun. And as I have mentioned, for our calculation purposes we can assume that the sun's rays are parallel. Okay, so they arrive parallelly on earth. Okay, and point P is any point on the surface of the earth. Okay, maybe it is the point of the observer, right. Now, with reference to this, we define all these solar basic solar angles, starting with the latitude. Latitude is defined as the angle between the lines OP. Okay, line OP is nothing but the line joining the center with the point P. Okay, line OP, and the projection of OP on the equatorial plane. The projection of OP on the equatorial plane is nothing but OA. Okay, so the latitude is nothing but angle between OP and OA, that is nothing but angle AOP, that is this angle. Okay, so as you know, the latitude varies from 0 degrees to 90 degrees. When is it 0? When the point P lies on the equatorial plane, obviously the latitude is 0. Okay, and when the point P lies on the pole, this angle becomes 90 degrees. So, this is how the latitude is defined, and latitude along with the longitude completely specify the location of any point on earth. The second basic solar angle is what is known as hour angle, and this indicates the time of the day. So, how is this defined? Again referring back to the same figure, here the hour angle H is defined as the angle between the projection of OP on the equatorial plane. OP is nothing but the line joining point O, that is the center of the earth, and the position of the observer P. Okay, and its projection is, as I have said, is OA. So, hour angle is nothing but the angle between OA and the projection of the line joining the center of the earth to the center of the sun. Now point O is the center of the earth and point O dash is the center of the sun. Okay, so the projection of O dash on the equatorial plane is nothing but AB. Okay, so that is the projection of O dash on the equatorial plane. So our angle is nothing but the angle AOB. Okay, that is the angle between OA and OB. Okay, that is this angle, right. Now at solar noon, when the earth rotates and when point P comes at this point, you find that the our angle is 0. Okay, and the our angle varies from 0 at solar noon to 360 degrees. Okay, because it rotates in one day, right. 360 degrees in 24 hours. Okay, because it makes one rotation in 24 hours. The third basic angle is what is known as declination, and declination indicates the day of the year. Again we refer to the same figure, and declination D is the angle between the line joining the center of the earth O and sun. Okay, that is nothing but the line O dash and its projection on the equatorial plane. The projection of line O dash on equatorial plane, as I have already discussed, is OB. Okay, so declination is nothing but angle between OB and O dash, that is nothing but angle D. Okay, and since this angle, that means earth is tilted 23.5 degrees. Okay, you have an angle of tilt of 23.5 degrees. You find that for northern hemisphere the declination varies from plus 23.5 degrees on June 21st to minus 23.5 degrees on December 1st, and this will be exactly reverse for the southern hemisphere. Okay, this will be clear with the help of this picture. As I said, this is the orbital motion of earth around the sun, and this is the summer solstice, that is on June 21st. On June 21st, as I said, for northern hemisphere your angle of declination is plus 23.5 degrees, and on September 21st and on March 21st, that means at the two equinoxes the declination is 0 degrees. Okay, and on December 21st, that means on winter solstice, you find that the declination D is minus 23.5 degrees. Okay, this, as I said, remember that this is for northern hemisphere. This will be very clear if you look at this picture. For example, take just summer solstice and winter solstice, that is June 21st and December 21st. This is the equatorial plane of the earth. Okay, and since this angle is 23.5, this angle is tilted as 23.5, the declination is nothing but this angle. Okay, so this is also 23.5 degrees. Okay, so by convention we take this as plus 23.5 degrees centigrade, and on winter this is your equatorial plane and this is your angle of declination. Okay, the line joining point O and this and its projection on equator. Okay, so this angle is minus 23.5 on December 21st. Okay, so it varies from plus 23.5 to minus 23.5 through 0 degrees, and it is 0 degrees at the two equinoxes. And the hour angle, so you can see now that the basic solar angles depends upon three important parameters, that is what is the location of the surface on earth, which is indicated by the latitude, and what is the time of the day. Time of the day is specified by the hour angle, and what is the day of the year. Okay, day of the year is indicated by your declination. So location, time of the day and day of the year, these three define three basic solar angles: latitude, hour angle and declination. Okay, and the hour angle, it is very important to keep in mind that the hour angle is based on what is known as local solar time. What is local solar time? Since the earth's orbital velocity varies throughout the year, the local civil time, which is based on our clocks, either mechanical or electronic, is different from the local solar time. So local civil time is what is the time shown by your watch, whereas the local solar time is, for example, time shown by, let us say, a sundial. Okay, so this is the time shown by a sundial. You will find that these two will be different. Okay, they are not exactly equal, and the difference between the local civil time and the local solar time is what is known as equation of time, or EOT. Okay, and empirical equations for EOT are available. So if you know the day of the year, you can calculate what is the equation of time for a particular day. Okay, it's taken as constant for a particular day, so you can calculate EOT as a function of the day of the year. Okay, if you know the number of the day, you can find out EOT, and the mean monthly mean values of EOT are also available in tabular form. So if you look at ASHRAE handbooks or anything, you will find the values of EOT. Okay, and at any location, the local solar time LST is given by this expression. LST is the local solar time, which is equal to LSTT. This is the local standard time. Okay. EOT, as you know, is nothing but equation of time plus 4 into LON minus LSM. LON is nothing but the local longitude. LSM is a local standard meridian. Okay. Let me give a very simple example. For example, for the city of Kolkata, Kolkata is located at 22.82 latitude, north latitude, and its longitude is 88 degrees 20 minutes east. Okay, this is the longitude, right? And the local standard meridian for India is 82 degrees 30 minutes, 82.5 degrees. Okay. So this is the data, and we would like to find out on October 21st if the local standard time is 9 AM. Okay, then what is the local solar time for Kolkata? Okay. So for this particular day, that is October 21st, from the empirical equation for EOT or from the table for EOT, you will find that the equation of time is given by 15 minutes. Okay, so EOT is given as 15 minutes. So the local solar time is nothing but local standard time plus 15 minutes. 15 minutes is your EOT. Okay, plus this is the correction for longitude variation between the LSM and LON. Okay, so our local longitude is 88.33 degrees, whereas the local standard meridian is 82.5 degrees. Okay, so this is the correction for that. So if you substitute the values, you find that local solar time is now 9 hours 38.32 minutes, whereas the local standard time is 9 AM. Okay, since this is 9 hours 38.32 minutes in the morning, the corresponding hour angle is 324.6 degrees centigrade. How did I calculate the hour angle? As I said, at noon. Okay, noon means let us say 12 o'clock. Okay, 12 o'clock solar time, solar noon, your hour angle is 0. Okay, so for example, at 1 PM, the hour angle is equal to 15 degrees centigrade. How is it so? Because it makes the hour angle varies from 0 to 360 degrees in 24 hours. Okay, so 1 hour is equivalent to 15 degrees. So if it is if you are starting with noon, then afternoon it will be starting with 0 at noon. Afternoon hours will be, let us say 3 PM means 45 degrees. Okay, 4 PM means 60 degrees, like that. And if you proceed in that manner, you find that in the mornings, for example 9 AM, 9 AM means 3 hours before solar noon. Okay, that means it is 360 minus 45, that is 315 degrees centigrade. Okay, so now the local solar time in this example is 9 hour 38.32 minutes. So the solar angle is 324.6 degrees. Okay, so that's how you can calculate the hour angle. So what you have to do to calculate hour angle is to first find out what is the local longitude, and you also should know what is the local standard meridian, right? And then if you know the local standard time and equation of time, then you can calculate, first you should calculate the local solar time, and once you know the local solar time, you can calculate the hour angle, because 1 hour is equivalent to 15 degrees. Okay. Okay, so the hour angle, as I said, is based on local solar time, and the declination varies in an approximately sinusoidal fashion. I have mentioned that the declination varies from plus 23.5 degrees to minus 23.5 degrees, and the variation is almost sinusoidal. Okay, so you can fit in an empirical equation. So this is an empirical equation for declination. Okay, declination d in degrees, this in degrees, it's all the angles are in degrees. Okay, this is very important, keep in mind. Okay, so your unit should be consistent. So declination in degrees is given by this empirical equation 23.47 into sine 360 into 284 plus n divided by 365. What is n? N is the day of the year counted from January 1st. That means January 1st n is equal to 1, January 2nd n is equal to 2, like that. So, December 31st n becomes 365. Okay. So, if you know the day of the year, you can easily calculate the declination using this equation. Okay. And from this equation you will find that on June 21st, okay, on June 21st you find that declination D is approximately equal to 23.5 degrees, and on December 21st, okay, this is equal to minus 23.5 degrees. Okay. For example, I want to calculate the declination for March 6th. Okay. March 6th happens to be the 65th day of the year, that means n is 65. So, all that you have to do is substitute the value of n here. So, you will find that the declination on March 6th is minus 6.4 degrees, okay, from the above equation. Okay, so these are the basic solar angles. Now, let us look at derived solar angles. In addition to the basic solar angles, several other angles required for solar radiation calculations are derived. First one is what is known as altitude angle. So, let us see what is this altitude angle. Okay, let me explain this figure. Let us say that this is an horizontal plane. Okay, so this is the point P is the position of the observer. Okay, and let this be the north and south sides, and this is the west and east sides. Okay, so you have north, south, east, west, right? And this is the path of the apparent sun path. That means this is the path of the sun as it appears to the observer, who is located at point P. So, as you can see that sun rises at this point. Okay, sun rises in the east and follows this path. This is for a particular day. Okay, this path is not constant; it varies again from day to day. So, for a particular day, let us say that this is the sun path. So, it rises in the east and it sets in the west. Okay. Now, with reference to this figure, what is the altitude angle? Altitude angle is given by beta. Beta is the angle between sun's rays and its projection on a horizontal plane. So, this is your sun ray, this is your sun, and this is the sun ray. So, beta is nothing but the angle between this sun ray and its projection on the horizontal plane. The projection of the sun's ray on horizontal plane is this. Okay. So, altitude angle is nothing but this angle, that is beta. Okay. So, as you can see that beta is 0 at sunrise. Okay. So, at this point the sun ray, the direction of the sun ray and its projection coincide. So, beta will be 0. Similarly, beta will be 0 at sunset. Okay. So, at these 2 points beta will remain 0, and it reaches maximum at solar noon. Okay. In fact, that is the definition of solar noon. At solar noon you will find that the altitude angle is maximum. So, this is the first angle. The second angle is what is known as zenith angle. So, zenith angle, I am sorry, this should have been psi, this is okay. Zenith angle is given by this symbol, is the angle between sun's rays and the surface normal. Okay, sun rays, as I said, this is the sun ray, and the normal to the surface at point P is this. Okay, so the zenith angle is nothing but this angle. Okay, so this is the zenith angle. Obviously, zenith angle plus altitude angle should be equal to 90 degrees. Okay, so this angle is equal to 90 degrees. That means the zenith angle is equal to 90 minus beta. So, if you know the altitude angle, you can find out the zenith angle easily. Next important angle is what is known as solar azimuth angle. Again we refer to the same figure, and the solar azimuth angle gamma is the angle between the north and the projection of sun's rays onto the horizontal plane. Okay, so what is so as I said, this is your north direction. Okay, so azimuth angle is nothing but this and the projection of sun's rays onto a horizontal plane. The projection of sun's rays onto a horizontal plane is this line. Okay, so the azimuth angle is the angle between this line and this line. Okay, so as you can see, that is nothing but this angle. Okay, this angle is given by gamma, and this is measured in counterclockwise direction. Of course, this varies, this convention varies from textbook to textbook. Some people define the solar azimuth angle with reference to the south direction. Okay, some people define it with reference to the north direction, and sometimes it is defined in terms of the clockwise direction from north, and in some books it is defined in terms of anti-clockwise direction from the north, and in some other books it is defined for forenoon it is in the clockwise direction, and for afternoon it is in the anti-clockwise direction. So the definitions vary, but basically once you have this diagram it is easy to understand and it is easy to change from one convention to the other convention. Okay. So in this particular lecture I am following the convention of measuring it from the north in the counterclockwise direction. Okay. So this is the solar azimuth angle gamma. Now using analytical geometry it is possible to derive relationships between derived and basic solar angles. This is important, the relationships between various angles. Okay, so altitude angle beta. So beta, it can be shown that beta, the altitude angle beta is equal to cos L multiplied by cos H multiplied by cos D plus sin L multiplied by sin D, where L, as I have already discussed, is latitude, H is hour angle, and your D is declination. Okay. So you can see that the altitude angle is simply related to the basic solar angles of latitude, hour angle and declination. That means the altitude angle depends upon the day of the year, time of the day and the location of the point. Okay. And as we know, at solar noon the hour angle is 0, that means cos H is equal to 0, right. So when H is equal to 0, as you know, cos H is 1. Okay. Then you find that the altitude angle is maximum and that value is given by beta max. Beta max is simply equal to pi by 2 minus L minus D. Okay. This is your absolute value of L minus D, where L is the latitude and D is the declination. Okay. So once you know the latitude and declination, you can calculate what is the maximum altitude angle on any given day. For example, for Kolkata, again take the example of Kolkata. For Kolkata the latitude is 22 degrees 82 minutes north, and I want to find out what is the maximum altitude angle on June 21st. Okay. And as we know, on June 21st the declination D is 23.5 degrees. Okay. So beta max is nothing but pi by 2 minus 22.82 minus 23.5. Okay, you have to take the absolute value of that, then you will find that this is equal to 89.3 degrees. Okay, this is the maximum altitude angle, is almost close to 90 degrees. Okay, on June 21st for Kolkata, and you can see that the beta max is equal to 90 degrees when L becomes D. Okay. So D, as we know, is that means when the latitude becomes equal to declination, the beta max becomes 90 degrees. Okay. Next, there is another important information that you can get from this equation, that is that at sunrise and sunset we know that the altitude angle beta is 0. Okay. So beta is 0 at sunrise and sunset, as I have already explained to you. So we can find out what is the time of sunrise and sunset using this equation. Okay. How? If you substitute value for beta as 0 here, you can find out the hour angle at which sun rises and sun sets. Okay. And that hour angle is given by this expression. This is derived from this equation. Okay. This is derived from this equation by taking beta is equal to 0. So H naught is the hour angle at which the sun rises or sun sets. So that is given by cos inverse minus tan L into tan D, where L, as you know, is the latitude and D is the declination. Okay. Let me give a small example. For example, I would like to find out the sunrise, sunset and total sunshine hours at IIT Kharagpur on September 9th. Okay. So I would like to find out at what time the sun rises and the sun sets and what is the total sunshine hour, that means how many hours the sunshine is available at this particular location, which has a latitude of 22 degrees. Okay. That means L is equal to 22 degrees north. Okay. So first, as you have seen, H naught from the earlier this thing is tan okay. So, as you can see from this expression, H naught is cos inverse tan L into tan D. So, we have to find out what is the latitude and we have to find out what is the declination. Latitude is given as 22 degrees. So, I have to find out the declination on this particular day, September 9th. So, all that I need to know is what is the number of the day. So, if you start counting from January 1st, you will find that September 9th happens to be the 252nd day of the year. So, n is equal to 252. So, if you substitute n is 252 in the expression for declination, you find that the declination angle is equal to 4.62 degrees. Okay. So, if you substitute 4.62 degrees in this expression, you find that the hour angle at sunrise and sunset is equal to 91.87 degrees. Okay. Since each 15 degrees is equal to 1 hour, 91.87 degrees is equal to 6 hours and 8 minutes. Okay. Right. So, the hour angle is equivalent to 6 hours and 8 minutes. What is the meaning of this? This means that the sunrise takes place at 12 minus 6.08, that is 5.52 hours in the morning. This is the solar time, and sunset takes place at 12 plus 6.08, that is 6.08 pm, right. So, sunrise is at 5.52 am and sunset is 6.08 pm, okay, and both are with reference to solar times, and the total sunshine hours are nothing but 2 into H naught, 2 into H naught by 15, let us say, since H naught is in degrees, this will give you the total sunshine hours. Okay. So, you can see the usefulness of this equation. Okay. This simple and elegant equation can be used to find out at what time the sun rises or sunset at any location on the earth on any particular day. Okay. And you can also calculate the total sunshine hours. This information is very useful in the design of several solar energy equipment, and it is also useful in air conditioning for load calculations. Okay. So, this is the relationship between altitude angle and the basic angles and the usefulness of this equation. Now, let us look at the other equation, that is the equation for solar azimuth angle in terms of the basic angles. So, solar azimuth angle, this as I have mentioned is as measured from north in a counterclockwise direction, right. So, that is if you take that convention, then this is given by gamma is equal to cos inverse cos L into sin D minus cos D into cos H into sin L divided by cos beta. As you know, again L is the latitude, D is the declination, H is the hour angle and beta is the altitude angle. Okay. So, this is defined in terms of, again that means this is again a function of the basic angles only, because beta is a function of basic angles L, D and H, right. So, this you also have an alternate expression, this is also equal to sin inverse cos D into sin H by cos beta. These two expressions are equal, so that you can easily prove by using your trigonometric relations. Okay. So, this is the relationship between solar azimuth and other angles, and one important thing to note here is that solar noon, that means when H is equal to 0, gamma is 180 degrees, for L is greater than D, that means when the latitude angle is greater than the declination angle, then we have to take gamma as 180 degrees, and gamma should be taken as 0 degrees for L is less than D. Okay. So, this you must keep in mind. Okay. So, only for solar noon you have to keep this information, and gamma is not defined for L is equal to D at solar noon from this equation. Okay. Now, let us look at the incident angle of solar radiation, that is theta. So, as I have already mentioned, the incident angle of sun's rays theta is the angle between sun's rays and the normal to the surface under consideration. The angle of incidence theta depends on solar geometry and also on the orientation of the surface. For example, let us look at a horizontal surface, theta is equal to zenith angle. This can be shown very easily if you look at this figure. So, this is your horizontal surface, and by definition theta is your angle of incidence, which as I said is defined as the angle between the sun's rays and the surface normal. Okay, since this is a horizontal surface, this is a surface normal, and this is your angle of incidence, and it so happens that the angle of incidence for horizontal surface is also equal to your zenith angle. Okay, zenith angle, and as we know, phi plus beta is xi plus beta is 90 degrees centigrade, 90 degrees. So theta is equal to pi by 2 minus beta. Okay, so if the surface is horizontal, then once you know the altitude angle, you can easily find out what is the angle of incidence. How this information is useful? For example, I want to calculate what is the radiation incident on the roof, on a flat roof. Okay, a flat roof means it is a horizontal surface. So all that I have to do is on a particular day at a particular time, because it is a function of the time of the day, location of the surface, and the day of the year. Okay, so all these things, for these once you know these things, all that you have to do is you have to find out what is the altitude angle. Okay, so calculate the hour angle from the time of the day, calculate the declination from the day of the year, and from the latitude information calculate the altitude angle. Okay, once you know the altitude angle, the angle of incidence is nothing but 90 minus altitude angle. So you can straight away get the angle of incidence for a horizontal roof. Okay. Now let us look at vertical surface. The calculation of angle of incidence for a vertical surface is a little more complicated compared to a horizontal surface, because here, in addition to the solar geometry, we also have to consider the direction the surface is facing, whether it is facing east side or west side or south side. These things will come into picture. Okay, let me explain that with the help of this picture. Okay, so in this picture, this is the shaded surface, is the wall, okay, or surface under consideration. Okay, I want to find out what is the radiation incident on this particular surface, okay, which is shaded in red, right, and this is your south and north direction. Okay, and the wall is arbitrarily oriented, right. So this is north and south, this is your east and west directions, and let us say that at a particular point on a particular day, the sun is at this position, and this is your horizontal plane. Okay, and this line is nothing but the projection of sun's rays. These are the sun's rays onto a horizontal plane. So this is 90 degrees. So that from definition we know that this angle is beta, okay, which is nothing but the angle between the sun's rays and its projection on the horizontal plane. Okay, so we have already defined that angle beta, and we also have defined the incident angle. Incident angle is nothing but the normal to the surface. This is your normal to the surface, okay, and the sun's rays, that means this angle. So we have defined these two angles already, that is beta and theta. Okay, and we have also defined solar azimuth angle gamma, which is nothing but the angle between north and the projection of sun's rays on a horizontal plane, that is this angle. So these three angles have already been defined. So I introduce here two new angles, that is one is what is known as wall solar azimuth angle alpha, and the other angle is surface azimuth angle zeta. Okay, so first let us look at wall solar azimuth angle alpha. Wall solar azimuth angle alpha is defined as the angle between the normal to the wall, that means this line, this thick line, and the projection of sun's rays onto a horizontal plane. The projection of sun's rays onto a horizontal plane is this. Okay, so alpha, which is called as wall solar azimuth angle, is nothing but this angle, that is the angle between the normal and the projection of sun's rays onto a horizontal plane. So that is alpha. And I said we have also defined another angle called zeta, that is what is known as surface azimuth angle zeta. Okay, so surface azimuth angle zeta is nothing but this. This is defined as the angle between the normal, that means this line, this thick line, normal to the wall, and the south. South is this. Okay, so for this particular picture, the picture I have taken in this, this is your zeta. Okay, if the normal is somewhere here, let us say, then the zeta becomes this. That means zeta is always defined with reference to the south direction and the normal to the surface. Okay, the normal to the surface obviously depends upon the orientation of the surface and the direction in which the surface is facing. Okay, and the convention here is that it is taken as positive for west of south. That means for all these directions, this is the south. So on all these directions, you take zeta as positive. Okay, that means zeta varies from 0 degrees when it the normal coincides with the south, to 180 degrees when it coincides with the north. Okay, that means for this one it is 180 degrees. and in this direction, if it is facing in this direction, it varies from again 0 to 180 degrees through a negative this thing. That means this become, for example, if you take east, east is minus 90 degrees, okay, whereas west is plus 90 degrees. Okay. Similarly, if you consider, let us say, southeast, okay, southeast is minus 45 degrees, whereas southwest is plus 45 degrees, okay, like that. So, if you know the orientation of the surface, you can easily find out what is the value of zeta, and remember the convention followed, that is positive for west of south and negative for east of south. Now, you can find a relationship easily between alpha, that is surface solar azimuth or wall solar azimuth angle alpha, and the solar azimuth angle gamma, and surface azimuth angle zeta. Okay. So, if you look at this picture, this is 180 degrees, this total angle, okay, is 180 degrees. So, 180 degrees is equal to gamma, that means this angle, plus alpha, that means this angle, plus zeta. Okay, for this particular case. So, for this particular case, which happens to be the afternoon, because the sun is towards the west, okay, it has crossed the solar noon. Okay. So, this example is for afternoon, right. For afternoon, you find that gamma plus alpha plus zeta is equal to 180 degrees. Okay. That means alpha is equal to 180 minus gamma plus zeta, right. Now, for forenoon, the sun will be on this side towards the south, okay, sun will be somewhere on this side. Then you will find that gamma is equal to 180 plus alpha plus zeta. Okay. In such case, you will find that alpha is given by 180 minus gamma plus zeta into minus 1. Okay. So, that is why I have given this equation. This is the relationship, alpha is equal to f into pi minus within brackets gamma plus zeta, where f takes a value of minus 1 for forenoon and plus 1 for afternoon. Okay. Now, it can be shown that the angle of incidence, because ultimately this is what is important to us, on a vertical surface is given by this relation, theta vertical is equal to cos inverse within brackets cos beta into cos alpha. Cos beta, as you know, is altitude angle, and alpha is your surface azimuth, surface solar azimuth angle. Okay. And the expression, as you have seen, is a function of your gamma and zeta, right. So, if you know the orientation, that means orientation of the surface zeta, and if you know beta and other angles, you can find out gamma. So, from gamma and zeta you can find out alpha, and from your basic latitude, hour angle and declination, you can find out beta, and from this information you can find out what is the angle of incidence on a vertical surface, theta vertical. And where do you use this information? This information is required to find out what is the solar radiation incident on a vertical wall. Okay. So, both horizontal orientation and vertical orientation are very frequently encountered in air conditioning calculations, because most of the buildings will have horizontal roofs, and all the buildings generally have vertical walls. Okay. So, you have vertical walls and horizontal roofs. So, you have to use these two expressions for finding the angle of incidence of solar rays. Okay. Now, let me give a very general expression for arbitrarily tilted surface. Okay. Any surface, it can be horizontal, vertical or tilted. For this arbitrarily tilted surface, it can be shown, okay, first this is the arbitrarily tilted surface, and here we define another angle called as tilt angle. Okay. That is sigma. This is the tilt angle. Okay. And this is the surface which is exposed to your solar radiation. Okay. So, solar radiation is falling on this surface, right. So, the tilt angle is nothing but the angle between the horizontal and the surface, okay, that you can see here, and it can be shown that the angle of incidence on any arbitrarily oriented surface is given by theta is equal to cos inverse sin beta into cos sigma plus cos beta into cos alpha into sin sigma. Okay, so in addition to your beta and alpha, you also should know what is the angle of tilt in order to calculate the angle of incidence of sun's rays on any surface. Okay, as I said, this is a general equation and it can be used for any arbitrarily oriented surface. For example, for a horizontal surface, this tilt angle becomes 0, right, because this coincides with this, it comes here. So sigma is equal to 0. Once sigma is equal to 0, this vanishes and this becomes 1. So you will find that theta is nothing but 90 minus beta. Okay, so this also simplifies down to this expression, and for a vertical surface, sigma is equal to 90 degrees for vertical surface, because this surface becomes like this. Okay, 90 degrees. So when sigma becomes 90 degrees, cos sigma becomes 0. So you won't have this term, and sin sigma is 1. So it can be, you can easily find that theta vertical is equal to cos inverse cos beta into cos alpha. Okay, so if you remember the expression for the tilt angle on any arbitrarily oriented surface, then you can simplify it to other surfaces like vertical or horizontal surfaces. Okay. Okay, so calculation of angle of incidence is one major part of solar radiation calculations. Okay, so once you calculate, that is required because you want to calculate what is the radiation incident on a surface. But in addition to the, if you remember your earlier expression, in addition to the angle of incidence, we also have to find out what is the direct radiation, what is the diffuse radiation, and what is the reflected radiation. Several models are available, several solar radiation models, using which you can find out direct, diffuse and reflected radiations. In air conditioning calculations, normally we use what is known as an ASHRAE model. This is the model suggested by ASHRAE based on their data, okay, the data collected by ASHRAE, and they have fitted empirical equations to their data, and they have suggested certain correlations for estimating these radiations. Okay, so this is a very popularly used model as far as air conditioning calculations are concerned. Okay, so in this lecture I will discuss ASHRAE model. So first let us look at direct radiation. Direct radiation from sun is given by I subscript capital Dn, that is equal to A into exponential within brackets minus B by sin beta, and the units are watt per meter square. Here A is what is known as apparent solar irradiation, and it takes a value of 1230 watt per meter square for the months of December and January. That means basically for winter, in winter A takes a value of 1230 watt per meter square, whereas during summer, that means during say May, June, July, A takes a value of about 1080 watt per meter square. Okay, so if you want to do the solar radiation calculations for winter, you can take a value of 1230 for A, whereas for summer you can take a value of 1080. And the constant B is known as atmospheric extinction coefficient, and it takes a value of 0.14 in winter and 0.21 in summer. So if you know the values of A and B, then you can calculate direct radiation. Of course, you also have to know the altitude angle beta, okay, because here sin beta is there, so beta is the altitude angle. So from the knowledge of altitude angle and A and B, you can calculate the direct radiation on a surface, and the values of A and B are available in tabular form. When ASHRAE gives the values of A and B for each month, and they calculated this for 21st day of each month, and these values are tabulated and they are available in ASHRAE handbooks. Okay. Next comes your diffuse radiation from sky. Diffuse radiation is I subscript D, and according to the ASHRAE model, the diffuse radiation from a cloudless sky is given by ID. They relate this to the direct radiation and what is known as an angle factor. So ID is equal to C multiplied by I subscript Dn multiplied by F subscript Ws, where C is a constant and it can be taken as 0.135 for midsummer and 0.058 for winter. Okay. And F subscript Ws is called as view factor or configuration factor, and this is nothing but the fraction of diffuse radiation incident on the surface. Here I would like to tell one thing. This ASHRAE model assumes that the sky is cloudless. Okay, that means the calculations are strictly valid for a cloudless sky. This assumption is required because this model is based on the assumption that the diffuse radiation arrives at the surface uniformly. Okay, so it arrives at the surface uniformly. This is valid only when the sky is cloudless. If the clouds are there in the sky, then diffuse radiation will not be uniform. Okay. And this factor, as I said, the view factor is nothing but the fraction of diffuse radiation incident on the surface, and it can be very easily shown that F subscript Ws, that is the view factor, is equal to 1 plus cos sigma by 2, where sigma is the tilt angle defined earlier. So, for a horizontal surface the tilt angle is 0, so the view factor is equal to 1, that means it sees all the radiation, it receives all the diffuse radiation. Whereas for a vertical surface sigma is equal to 90 degrees, so cos sigma becomes 0 and the view factor becomes 0.5. That means the vertical wall receives only 50% of the diffuse radiation from the sky, whereas the horizontal surface receives all the radiation from the diffuse radiation from the sky. Okay. And the values of C are again available in tabular form. Finally, we have this reflected short wave radiation from the ground or from the surrounding surfaces. The amount of solar radiation reflected from the ground onto a surface is given by IR is equal to IDN plus ID. This is nothing but direct radiation plus diffuse radiation multiplied by rho z multiplied by F subscript Wz, where rho z is the reflectivity of the ground, which depends upon the surface nature of the ground or a horizontal surface, and F subscript Wz is what is known as view factor or configuration factor from ground to the surface. Okay. Again, by definition this view factor is nothing but how much fraction or what fraction of the reflected radiation is received by the surface. Okay. If the surface does not receive any of the reflected radiation, then its view factor is 0. If it receives all the radiation, then its view factor is 1, right. And it can be easily shown that Fwz is equal to 1 minus cos sigma by 2, where sigma is equal to tilt angle, as you know, and for a horizontal surface facing upwards sigma is equal to 0. Okay. So, sigma is 0 means your view factor is 0, whereas for a vertical surface sigma is equal to 90 degrees, that means view factor is 0.5. Okay. So, this is how using the ASHRAE model you can calculate direct, diffuse and reflected radiations from the known data. Okay. Once you know these things and once you know the angle of incidence, you can calculate the total radiation incident on any surface. Okay. So, at this point I conclude this lecture, and I will give an example on how to calculate the radiation in the next lecture. Thank you.